for inviting me to this very nice event. Like I said, like you said, actually, my name is Fabio Cuzzolin. I'm the director of this Visual Artificial Intelligence Lab at Oxford Brookes University in Oxford, UK. And today I'm going to tell you a little bit about this new Epistemic AI project funded by EU under the FET scheme that I'm coordinating, which I think relates very much to the topic of your seminar series. So what are the objectives of the project? I think probably I want to introduce the lab first. So this is the web page of our lab. And as you can see here, we do quite a lot of stuff. So we have multiple projects and we investigate various areas of research from uncertainty theory to artificial intelligence, more in general. For instance, we have this Epistemic AI project. We have a project on machine theory of mind with Cambridge Neuroscience. We have two active projects on surgical robotics or AI for healthcare, and one is called SARAS, funded by the EU, and then there's another one called Maestro, funded by the UK Research Council, but we're also working on neurosymbolic reasoning, continual learning, federated learning, zero-shot learning, and in computer vision, we've done a lot of work on human motion, human behavior understanding, action and activity detection from videos. We have a project on scene understanding with the company, and we do a lot of work in autonomous driving. We just recently created new data sets for event detection in autonomous driving, for surgical action detection in surgical robotics, and also continual learning, continual activity recognition, and continual crowd counting from videos. These were released as part of two recent events, a HKI workshop on continual semi-supervised learning and an ICCV workshop on road event detection. So here you can find some information on this road challenge at ICCV that we organized in mid-October. And before that, there was a first international workshop on continuous semi-supervised learning at HKI 2021. And at the same time, we also organized the A Challenge at MICI 2021, the top medical imaging conferences on multi-domain endoscopic surgeon action detection. More information about our research is available here. So these are the main fields we work on: uncertainty theory, computer vision, machine learning, AI, surgical robotics, and autonomous driving. And if you click on AI here, you have the more like AI-related projects, Epistemic AI, as well as the project Machine Theory of Mind, and the new project Neurosymbolic AI. This is in collaboration with Samsung AI in Cambridge. So going back to my slides, what about the EPI project? EPI is the acronym for the project. So this is funded by the Horizon 2020 FET Open Scheme, which, as you know, is a very competitive scheme. It used to be around 3 or 5% success rate. Now I think it's a bit better than that, but still very competitive. And we got it the first time, so we were very happy with that. Budget is a maximum of 3 million euros for a duration of 4 years. There's a consortium of 3 universities. There's Oxford Brookes, which is the coordinator with myself. There's KU Leuven and TU Delft. This is the website for the project. So if you click here, that will take you to the Epistemic AI website. We describe briefly the concept, but there's also some information about the work plan and different work packages, team, and so on and so forth. So you're very welcome to browse through the website for the project. So what is the concept? The concept is that current artificial intelligence is quite unable to deal with epistemic rather than aleatory uncertainty, which severely limits its development. So our objective is to reimagine AI through a proper treatment of the uncertainty that stems from our partial knowledge of the world, which is not quite captured by probabilistic methods that just model the aleatory uncertainty. So we propose to do this by injecting techniques from uncertainty theory This is the consortium, like I said. So there's three universities. There's ourselves as coordinators. There's KU Leuven and then TU Delft. There's a very good overlap, spread of expertise, but also overlap. So for instance, Co are experts in robust optimization and optimization theory in general. We have expertise in uncertainty theory and both uncertainty theory and AI. I actually did my PhD at the time, quite a long time ago, on uncertainty theory and random set theory in particular. Whereas Delft, as you probably know, they're very strong in AI and also autonomous vehicles. Several sub-areas are covered by multiple units, such as uncertainty theory, AI reinforcement learning, and autonomous driving. So this is the senior team. So at Oxford Brookes, there's me, and there's a senior lecturer, Andrew Bradley, who is the head of the autonomous driving research group. And the reason is that the new epistemic AI learning paradigms that we are going to create in the course of this project are going to be validated in the autonomous driving scenario. In KU Leuven, there's two professors, Hans Halle and David Moynes, and a senior research fellow, Kevin Sharat Madar, who is Kevin and I initiated this whole project at the beginning. In TU Delft, there is associate professor New York Smith, assistant professor Matti Spahn, and assistant professor Julian Koji. So what is the concept, which I think is the thing you're more interested in? So the project is based on a paradoxical principle that AI should first and foremost learn from the data it cannot see rather than the data that it can see. And this is to express the huge imbalance between the amount of training data that one normally has at disposal and the actual potential universe of data relevant to the problem that is actually out there but is not available for training. So this is illustrated in this diagram, I hope. So this is classical machine learning. So you have a model space, which is empty to start with. You observe some training data, and then using some optimization technique, you learn a model in the space that explains the training data and possibly a little bit about the data outside the training set. So this is called generalization power in machine learning. So and usually, models can generalize to data outside the training set, but it's quite uncertain how much they can do that. To what extent they can do that, to other domains their power of explanation extends to. In epistemic AI, the point of view is quite different. We start from a state of ignorance, so all models are possible before we observe any data. Then after we observe the training data, we only learn constraints on the set of models that are compatible with the training data itself. So basically, we use data to refine our uncertainty about which is the correct model, what is the correct model for the data. So that's hopefully the research hypothesis is a set of models learned using uncertainty theory can explain a much bigger fraction of the universe of possible data related to the task. So not just the training data and not just data that is a bit similar to the training data, but not so much, but quite a big fraction. So in epistemic AI, ignorance is the fundamental stance. So we start from the point of view of being ignorant about the project, and we only use data to temper ignorance in the light of the new evidence. So this translates into a new learning paradigm which seeks sets of models that are compatible with the training data, like I said here. So here I drew like linear constraints on the space of models, but it could be a different kind of constraints. So you can see epistemic learning really as a form of set-wise learning data. What is uncertainty theory? I think a lot of you will be familiar with this from what I hear, but nevertheless, I think this needs a bit of an introduction. So this is done, the mathematical tools that allow us to do this epistemic learning or set-wise learning is uncertainty theory. Uncertainty theory is an array of formalisms that have been devised to encode what people call second order or epistemic uncertainty about the phenomenon. So this is uncertainty about the correct probabilistic process that generates the data. For instance, if I'm tossing, I'm rolling a die, is my die not fair? And if so, what are the probabilities of its faces? This is sometimes called, the probability that generates the data is called domain distribution in machine learning. This is in opposition to aleatory uncertainty. For instance, if you have a die and you know the probability of the faces, you roll the die and you're uncertain about the outcome of the experiment, but you know exactly the probabilities that govern the experiment. In epistemic uncertainty, you don't know the probabilities that govern the experiment, so you're uncertain about the model of uncertainty itself. That's why it's called second order uncertainty or epistemic uncertainty. Now, this is quite the situation in machine learning for we ignore what is the real shape of the data generating distribution. So we can conjecture it, but we don't really know it. So in machine learning, we argue that we are subject to a heavy epistemic uncertainty because we don't really know the probability that generates the data, and we still want to make inferences about it. So uncertainty theory models uncertainty using more complex measures than standard probabilities. Then they often amount to convex sets of probabilities, for instance, lower and upper probabilities, probability boxes, random sets, or Creedle sets. So I'm going to make a few examples in the next slide. There are other approaches that are less directly related to probability theory. For instance, there are behavioral interpretations of precise probabilities and so on. It's been developed in Belgium, in Hint. There's a strong group that does that. Epistemic AI takes its name from the fact that the goal is of not forgetting one's ignorance. And this goal is achieved by modeling epistemic uncertainty using uncertainty theory. That's why we call the project Epistemic AI, and people seem to like it. So can we see some examples of these uncertainty measures? So there's actually quite a lot of them, and they form some sort of hierarchy of encapsulating formalism. So there's not just a single choice. There are many possible theories one can use to model epistemic uncertainty. A very simple one is probability boxes that you can see here. So instead of having this a cumulative probability distribution, instead of having a single CDF, a single cumulative probability distribution, you can have a lower CDF and an upper CDF. That's that theory, that concept is called probability box. You can have generalization of measures, probability measures called monotone capacities, in which every set is assigned a measure, A, but instead of being additive, these measures are just monotone. So if A is included in B, then the measure of B must be not smaller than the measure of A. That's why these are called monotone capacities. So you can easily see this standard probability distribution, a special case of both probability boxes and monotone capacities. The framework I've mostly worked on in the past. I did my PhD now, actually, and I think it's the most promising is that of random sets, represented here a little bit. And this is a cloaked die, so in which a couple of faces, phase one and phase two, are cloaked. So when you roll the die and you get the cloaked phase, you don't really know what the outcome was. You only know that the outcome is either set phase one or phase two, but you don't know which one. So this is an example of a random variable that outputs sets of observations instead of single observations. So and random variables that output sets are called random sets. So they're another straightforward generalization of random variables and probability distributions. Like I said, these uncertainty theories are actually, there's quite a zoo of them. There's a lot of them, and they form most of the hierarchy or clusters, which I try to depict here in a survey paper that I'm going to publish soon. I also have a book. Let me just digress for a second, but if we go to my website, this is a book titled The Geometry of Uncertainty, which I published with Springer. It was released in January this year, and it's quite an extensive compendium of all uncertainty theories and their geometry. So it's 860 pages, I think. So it's a very extensive book. So the idea was to make it a compendium of possible approaches to uncertainty theory, and in particular analyze their geometry, because the contribution of my PhD was a geometric approach to probability in which every measure can be represented as a point of a geometric space, and then you can reason in this space using geometric tools. So this picture here shows a little bit what the clusters of theories are. So you have measures of functions. I mean, starting from here, generalized measures on events. So for instance, you have capacities. Among capacities, you have belief functions, you have random sets, you have two monotone capacities, and you have standard probabilities, actually. You have methods that robustify probability theory, so like lower and upper probabilities, probability intervals, Credal sets, which are convex sets of probabilities, P boxes. You have approaches based on generalized sets, like RAP sets or fuzzy sets, or Zada's generalized theory of uncertainty. You have behavioral probability approaches like lower and upper previsions, definitive prevision, and recently developed Schaefer behavioral probability theory. And then you have higher order probabilities like probabilities on fuzzy sets, probability functions on fuzzy sets, and the algebras, meta probabilities, Dirichlet distributions, and other second order distributions. So there's a bit of a zoo, like I said. But in the course of this project, we're mostly going to focus on random sets and possibly P boxes and Credal sets. So these 2 or 3 approaches. So this is another diagram of the entire research project, the program for the project. So the idea, like I said, is to revisit the way uncertainty is treated in AI, including the way it's done, optimization is done, and inject these advances into the 3 main subfields of machine learning. So all of them. So unsupervised learning, statistical learning theory, supervised learning, and reinforcement learning. So it's quite wide, the scope. So this depicted here, you have an uncertain world. We have missing data, hidden human behavior with hidden reasoning processes, scarce data, limited or biased training sets. That induces epistemic uncertainty, so that can be treated by theories, epistemic uncertainty. You can actually formulate optimization frameworks under epistemic uncertainty, and then you inject all of those frameworks into supervised learning, for instance, by creating epistemic GANs or adversarial networks. We use these theoretical results to provide generalization bounds for epistemic learning, so epistemic generalization theorems. We want to generalize supervised learning by doing domain adaptation or doing CNNs that output random sets instead of traditional likelihoods. And we also want to generalize reinforcement learning by generalizing the Markov decision process framework by allowing convex sets of probabilities as transition probabilities rather than single probabilities, derive robust reinforcement learning algorithms and robust inverse reinforcement learning algorithms. Finally, we're going to validate all these new learning frameworks in autonomous driving, things like understanding the behavior of other road users, transition between manual and automated behavior, and so on and so forth. So the objectives are to create a novel mathematical framework for optimization and epistemic uncertainty, outputting sets of models, like I said, and leveraging techniques from theories of second-order uncertainty to reformulate unsupervised learning in this epistemic optimization framework. Sow the seeds of a new epistemic learning theory that replaces statistical learning theory, classical statistical learning theory, and derives robust generalization bounds to bring about a robust epistemic theory of supervised learning and reinforcement learning, to validate these 2 epistemic AI paradigms for autonomous driving, and to foster, finally, last but not least, to foster an ecosystem of academic research, industry, and societal partners throughout Europe. And this an example of that. There are 4 work packages, where package 1 is formulating an optimization framework inspired by the principle of knowing not to know. And this means injecting epistemic uncertainty in the loss function and the constraint. So, for instance, if you have a p-box, so if you have constraints in the objective function, the formula p-box, how does the optimization framework change? So you can do point-wise optimization of the epistemic uncertainty or optimization of the epistemic decision theory. This is mainly the work of K.O. Leuven. So they're in charge of devising this new framework for constrained optimization under epistemic uncertainty. Work package 2, which is the one most related to the topic of this workshop, is epistemic AI itself. And there's, as you can see, there's a bunch of tasks we set to ourselves. So learning set, paradigm for learning sets of hypotheses or models instead of single models, epistemic statistical learning theory, supervised, unsupervised reinforcement learning, inverse reinforcement learning, and so on. So these are a couple of pictorial representations of what I mean. So for instance, if you have like a binary classification, you want to find a linear separator between the two, right? So you can see here a training set, even a separable training set, only determines a convex set of possible linear boundaries between the two classes. So if you do like a traditional SVM, you estimate the maximal margin boundary, linear boundary between the two. But our point of view is that there's no need to do that. Actually, you should acknowledge the epistemic uncertainty associated with the training set and work with the convex set of boundaries instead. This picture here depicts the fact that in our work on epistemic statistical learning theory, we do no longer assume that the training distribution and test distribution are the same, although unknown. But for instance, we replace that assumption with the assumption that maybe they belong to the same convex set of distribution or Credo set, or the same random set, for instance. So the question is, what kind of generalization bounds we can get from this assumption? Work package 3 is the validation one, so in which we generate proof of concept level demonstrations of the proposed. You can know that FET opens are not really about technology. I mean, they're about technology transfer, but they're expected to produce results at proof of concept level, so TRL like 3. Nevertheless, we want to be as accurate as possible. So we have 3 validation domains. One is domain shift from simulated to real world tracking situation. One is autonomous racing cars, because in Brookes, we have a very strong track record on formula student competition, as they call it. So team of students that compete by creating racing cars. In the past, they were like traditional racing cars. Now they're electric cars. And next step is autonomous racing cars. So we actually, past 3 years, we got second place, first place, and third place nationwide on this. So we're very strong on that. And also the last validation domain is understanding and predicting road user behavior. This builds on the road event data set that I told you about at the beginning. So what about epistemic artificial intelligence? What are the tasks involved? So the first task is learning sets of hypotheses. So like I said, the principle is that from the training set, instead of learning a single model, you learn a set of models. And this is depicted in the picture that I just explained on the right. So I see epistemic learning as a form of set-wise learning, basically. So from mapping from data sets to sets of models in the model space. Now, they can be efficiently handled through their vertices, hopefully, but you need to devise suitable performance measure for sets of models instead of single models, and find out how these sets of models, the performance of these sets of models compare to classical methods, right? So this is an entirely new paradigm for learning, although there are recent papers that propose learning lines of models. We need to efficiently manipulate sets of models, and we need to investigate this question of what performance measures are best used for sets of models. And this would allow us to derive generalization bounds in an epistemic statistical learning theory or epistemic learning theory that generalizes classical statistical learning theory, SLT. You know, the SLT derives generalization bounds on model performance, typically by assuming that both training and test data are generated by the same, albeit unknown, probability distribution. we want to derive new bounds starting from the assumption that training and test data come from the same uncertainty measure rather than probability distribution. So that can be a probability box, can be a cradle set or a random set. Technically, this is a very challenging problem. It requires deriving suitable concentration inequalities for certain measures. If you glance at those generalization bound theorems in statistical linear theory, you know they use things like Markov inequalities or Chebyshev inequalities from probability theory. So this is a hardcore mathematical work. We need to work out what concentration inequalities apply to uncertainty measures and derive generalization bounds based on those. Like I said, my PhD topic was on generalized probability theory. So I'm kind of a crossover between an AI guy and a statistician or a probabilist. So that's where this is coming from. From the learning paradigm point of view, the first step is to do supervised learning, epistemic supervised learning. We're going to concentrate on deep networks, obviously. And this is represented a little bit over here. So you have a DNN, a deep neural network like CNN. But instead of outputting likelihoods for, this is a classifier, let's say, instead of outputting likelihood for single classes, you want to output scores for sets of classes. So your output neurons are going to be associated with sets of possible classes. So if you output a score for each set of classes, you have a random set as an output. So what we want to design is deep neural networks that output random sets instead of likelihoods. And these random sets, they correspond for each class to a lower likelihood and an upper likelihood. And then the problem becomes, how do you train this epistemic deep network? You need to devise a loss function that applies to random sets. So this is likely going to be a generalization of classical closed entropy or focal loss, if you're familiar with these things. We are also looking at epsilon contamination models that robustify Bayesian networks, basically. You can learn networks under Bayesian uncertainty, under parameters, under these epsilon contamination models. Gaussian smoothing networks for robustness, and also we are looking at extension of the dropout technique to produce ensembles of networks. Like I said, epistemic learning is a form of set-wise learning. So our objective is to learn sets of models from data. Efficiency is going to be key because we cannot really output neurons, have an output neuron for each possible sets of classes because this is exponential in complexity. So we need to select efficiently sample the sets we want to output values for, using, for instance, Shapley values from game theory. In unsupervised learning, we're going to focus mostly on generative adversarial networks. So if you're familiar with GANs, you will know that they work by sampling random Gaussian noise as input. And then they have an adversarial loss, which is an expectation. So there's two ways we can generalize GANs. One, by sampling from a random set or another uncertain measure instead of a Gaussian noise in the input. And the other one is by generalizing expectation using imprecise probabilities. So you're going to have a loss function, which is going to be a lower or an upper expectation of the classical loss. I don't wanna get into the detail, but I think you got the gist. In reinforcement learning, this is a partially observable Markov decision process. So based on the state and the action of the agent, you learn the reward, and then that will take you to the new state with a certain probability. And you also have a certain probability of observing, because the world is only partially observable. You only have a certain probability of observing the certain quantity given the state of the world, which is hidden. And this is directly generalizable if you replace standard probabilities and standard transition probability. So instead of having a single conditional probability of transition into a new state given the previous state and the action, you have a convex set of probabilities, transition probabilities. And in the same way, you're going to have a convex set of emission probabilities, so observations given the state. So what kind of, this is kind of a imprecise or epistemic graphical model, right? So we can found an entire theory reinforcement learning based on this epistemic graphical model. And for instance, one of the purpose of the project is to generalize Bellman's equation. There has been some sparse work on graphical models with imprecise probability, especially hidden Markov models, but not so much. So we'll start from those, but there isn't a lot of done yet. We can examine various alternatives to uncertainty measures, and again, we're going to keep an eye on efficiency. For validation, this is the road event awareness dataset for autonomous driving that we just released. It's the world first dataset that kind. We annotated 22 videos from the Oxford Robocar dataset in a multi-label way. So every road event is a touch agent label. So for instance, car, an action label, the car is turning left, turning right, and the location with respect to the autonomous vehicle. And this is a data set that we designed for testing prediction capabilities, detection capabilities, so the ability to detect road agents like cyclists or pedestrians, but also detect actions, turning left, turning right, road events more general and even more in general situation awareness. This the road at ICCV workshop that we organized this year. We have a paper under major revision at PAMI on that. Further extensions, and then I'll conclude. The original epistemic AI proposal didn't really contemplate continual learning, so it was just about learning from training set in an offline way. So a natural extension of that is continual epistemic learning, where you can imagine you have a series of sets of data over time, in a streaming way or occasionally. Then you keep the objective of this is the concept here that you keep refining the set of models, the model of the data in the light of new evidence. You get a new batch of data, you refine the uncertainty, you get the new set of models, and you keep doing that. And there are two different ways of doing that. One is, for instance, by using combination rules from uncertainty theory. So this say, for instance, a random set in the space of models, and there's another random set. You combine them using a combination rule, and you move on. And you keep combining them using combination rules. The alternative is that you update the vertices of the sets of models using the new data, and you keep going. So one thing I want to do in this follow-up project funded by the UK Research Council, this is pending, is comparing these two different ways of updating epistemic uncertainty about the model based on new data. And another extension is neurosymbolic learning. There's a strong interest towards neurosymbolic methods. These days, they integrate learning and reasoning in a single coherent framework as one of the elements of future artificial intelligence. And once again, epistemic uncertainty also affects neurosymbolic reasoning. So this is kind of depicted here. You have your neural model and you have your knowledge you want to inject in your neural model, but both of them are affected by uncertainty. In the end, you want to get out of this, you want to get common sense predictions that meet your logical constraints under the uncertainty. So you can see here the diagram is a bit of an extension of what I presented before when I talked about deep epistemic networks. So you have your network that outputs random sets or lower likelihoods subject to an epistemic loss that is used for training. But then on top of that, you can have a second stage in which you have a logical theory that reasons on these epistemic facts using a certain knowledge base. And in the end, you're going to get an epistemic framework that outputs predictions that meet with a certain probability or a certain, say, lower probability, the facts that are contained in the knowledge base. So this is a cascade of an epistemic neural network and a theory for reasoning with epistemic logic. I think I'm done. So this project has received funding from the European Union 2020 Research and Innovation Program under grant agreement. and then 64505 E prime. Thanks for your attention. I'll stop sharing now.
Thank you, Fabio.
Open the floor to questions.
Very broad and rich presentation, yours. So let's open the discussion. Whoever likes, just switch on your mic and ask a question or comment, or you can use chat if you want.
Don't be afraid.
Do so. So I can see Stefan's video. So
hello, Fabio.
Hello, Stefan. Nice to meet you.
Nice to meet you too. Can you hear something? Yes, apparently. That's good. Thanks a lot for the presentation. It was very, I don't know how to say, very comprehensive and gives a really nice idea about areas that personally I had no idea at all about. So a lot of it, I wouldn't probably need a 200-hour course, but I have something that I think maybe I understood could be connecting to something we're doing. It was the mode when you were talking about, and maybe I'm using the wrong word, so please forgive me, but something like model selection or something going in that direction, where you have like a battery of models or maybe a lineage of models or a hierarchy. I'm not sure how they are organized. And for our applications, which are quite a lot in biomechanics, where we have very little information, that's the first problem. So using statistics is not so easy because the amount of information is small, and the variability, which is not a good companion to having little information, is huge. So we have huge variability and little information or data, let's say. Little data and therefore little information, probably, in the data. And so we've been, a lot of people, I think, in the community are wondering how to select the best model for this, because, you know, you go to conferences and some people use model A and then others B and C, and everybody has a lot of good reasons. But I don't know that there is yet a way to do that in a, you know, in a systematic, beautifully elegant way, as I see that the theories that you work on seem very elegant and
yeah, I think you're in exactly the same kind of setting that I explained. So you have little data, and so you have huge uncertainty about what actually goes on and what should be the model used. So our point of view is that you shouldn't try to choose a single model if you don't have enough information, but you should work with constraints. So meaning, like, for instance, intervals of parameters. So by a set of models, I mean, for instance, you have a network but you don't know the values of the weights. So you have some certain intervals for these values.
Yeah.
So in general, the philosophy of uncertainty theory is that you should be respectful of the data that you have. You shouldn't be introducing additional hypotheses if you can avoid it. And which is not what people normally do. People normally
do Bayesian usually.
Yeah, no, I'm gonna model it like this, and the noise is Gaussian, and these components are gonna be condition independent. They start throwing a lot of additional assumptions on the problem. In the end, they do converge onto a single model, but possibly is a model that doesn't model at all the initial problem. So what we think is that you shouldn't be doing that. You should be, if the mathematics allows you to do that, you should be working with all the models that are compatible with your data. And that means like having intervals of parameters, for instance, or having a random set on the space of parameters, or there are some few papers in machine learning in recent years, last 1 or 2 years, that do like Bayesian uncertainty. So, for instance, even epistemic uncertainty. There was one in NeurIPS 2019 where they were using second-order Dirichlet distribution or Dirichlet distributions are distributions on the spatial distribution, so they're called second-order distributions. So there are ways to model epistemic uncertainty in a mathematically correct form without having to introduce additional assumptions. So this is what we were trying to shoot for in this project. I have tutorials on general uncertainty theory. I gave tutorials at UAI Uncertainty in Artificial Intelligence 2015 and also each guy in 2016. So on my website, I have the slides and also there's a couple of videos on the YouTube. So if you're interested in knowing more about that, I can even send you a copy of my book if you want. So start reading the introduction or something.
Oh, yes.
Or you can have your library buy it. I don't know. There's
yes, we will for sure do that. Yes.
But I'm very welcome. I mean, I'm very happy to provide more information if you want to know more about it. You think it can be interesting. Something from what you said, it is very relevant to your kind of problems.
All right, thank you very much. I'll leave the floor to others for now, but I have some other points.
Hello, Fabio. This is Vasilis Krokos. I hope that you can hear me.
Yeah, I can.
So I'm doing, thank you very much for your presentation. It was very interesting. And I'm doing my PhD in deep neural networks and basically Bayesian neural networks. So I'm kind of familiar with the things that you are talking about, but to be honest, I was like working in a very reduced space, let's say, of what you said today. And based on your discussion now with Stefan, and you said like at least in what I am doing, and like I was reading papers on how to do like a Bayesian inference, like have a Bayesian neural network for regression tasks in like mechanical engineering. It is true that we take like we say, okay, the noise is Gaussian, the parameter of the distribution of parameters, so in each layer is Gaussian. Yeah. And we do take we do assume all these things. And you said you implied that you are working on other things and that do not take these assumptions. And I was like, I was wondering, like, are these things like practical, like in terms of training? Do they converge? Is it more expensive? Maybe it's like 3 times more expensive than training a deterministic neural network. So there should be a trade-off there. And I was just wondering if you can comment in
These
any
are
of these
good
things.
questions. I mean, this is what the project is supposed to be about. So the project just started. So we mainly just hired the people, PhD students and the researchers. So the work is starting kind of now. But these are all the questions that we want to answer. So efficiency, like I said, you can avoid committing to specific distributions and work with sets of distributions, or those sets are complex sets of distributions, or random sets or key boxes. But many of those are going to be more computationally expensive than working with standard probabilities. So you need to sample efficiently. So you can do extensions of Monte Carlo sampling, for instance. You can do like I mentioned very briefly, Shapley values are a way of measuring the relevance of different factors in game theory, but also they can be hopefully employed to select which sets we want to output a probability for, and keep a fixed budget, so that we fix a budget and then we work always with the same number of sets, and we just change them over time, but we don't that doesn't blow up. So there are ways of enforcing a fixed budget. I think this is one of the things especially because networks need to have a fixed topology, so you cannot have a variable. I mean, you could. I mean, there are studies on variable topologies, but I think it's desirable to work with topologies that are fixed. So you're going to have a fixed number of output neurons, and then you're going to change the meaning of those over time.
I see. Okay.
But all the questions that you pose are the questions that we want to answer. So there are like I hinted at, there are lots of mathematical frameworks for modeling uncertainty in a more general way than probability theory, and a lot of them actually generalize Bayesian reasoning. So you don't have to abandon really Bayesian reasoning. Bayesian reasoning is just a special case. So if you work with classical probabilities and conditioning events, you go back to Bayesian reasoning. So for instance, random set theory, Bayesian reasoning is a special case of belief function reasoning or random set theory. So you just extend the mathematical framework. You don't really abandon the principle of revising your knowledge based on new evidence. So the principle remains exactly the same. You have a prior or you don't have a prior. The good thing about uncertainty here is that you don't have to assume a prior. So one of the main advantages compared to Bayesian reasoning is that you're not forced to set a prior. So if you don't have a prior, you have complete ignorance. You just assign probability 1 to the entire sample space. So you avoid biasing the reasoning process from the start by picking the wrong prior. And then you just you get new knowledge, you keep refining your knowledge over time, just like you do in Bayesian reasoning. But instead of maintaining a single probability at each point in time, you're going to have whatever measure you fit.
I see. One more question, maybe just a comment from you. Like in these weekly meetings that we have, a lot of times we have discussed dropout as a way to get uncertainty, and also Sorab, I think he worked a little bit with that, and we were discussing in the context of like it's kind of like almost free to get uncertainty with dropout. So in terms of training, you don't need to change your training procedure, sorry. And but we like, what are your thoughts on that? Do you think that this is like a good method to get uncertainty in neural networks?
I think it's potentially quite interesting. One of my students, I think one of my students she's actually looking into this as we speak. So possible using of dropout. I mean, what I found interesting of dropout was that you get this if you depending on what you drop, you get a different model, right? So from the original source model, you can easily generate an ensemble of models. The thing is that these are like discrete ensembles. So, you have, I don't know, a constellation of models instead of a continuum of models.
Okay.
So it's a slightly less general than what I was trying to convey in the slide. So, but it is, I think I see it as a sort of an intermediate step towards full epistemic description. So by doing DOPRA, you get like constellational models, like 5 models, I don't know. And then you can make predictions using these 5 models. You're going to have a spread of predictions. You can measure the spread of these predictions and assess uncertainty in terms of the spread of these predictions, of this constellation of point-wise predictions. So it's kind of an intermediate step in my mind between classical learning and so Sorab is asking for references to random sets for network weights. Yeah, so I'm not quite sure there are many references actually. So this is why they accepted this PET project, because it was, PETs are supposed to be blue sky thinking and change of paradigm sort of.
Perhaps your book, is it a good reference for this?
Good. Yeah, the book is not about okay, there is a chapter on application to machine learning, but it's not about machine learning per se. So it's about the mathematics of uncertainty theory. So okay, I can show. If you send me an email afterwards, I can surely send you material. So the book is here. I'll put it in the chat, and then I have the tutorials. Let me just look them up for you. There's this Ichkai 2016 tutorial. It's sort of 450 slides, so it's actually quite extensive. And also there's a shorter UAI 15. Sorry, UAI 15 video on the YouTube. You can start from those, but these are about the generalities of uncertainty theory rather than epistemic AI per se. There were some papers that I saw recently about this. So there's this evidential Dirichlet. So this NeurIPS 19 paper, oh, this one, yeah, actually, yeah. I don't know if you saw it in your work. If you're working on Bayesian uncertainty, you might have seen it. So this a paper by Murat Sensoy and co-authors from I think NURBS 19, and there's some papers by Thierry Donneau, on networks they use belief functions. So let me just see if I can find one quickly. Belief, no. Neural network classifiers based on time series.
Maybe.
This is a pretty old paper, but there's a more recent one. There's more recent one, I think.
But yeah, thanks a lot for this.
Maybe.
There's
Hi, Fabio.
more. I can look up for more stuff in this as a start, I think.
Okay. Hi, Fabio. Thanks for the nice presentation. I have one question. From your general experience, what do you say that we have observed that when we replace the deterministic networks with the probabilistic ones, usually we see the loss of accuracy in the solution, and sometimes it's quite more. So can you comment on that? How it is in your applications, and how do you deal with it?
So I think that relates to the question of what performance measure one should use, right? Because I think networks that take uncertainty into account, should not be evaluated in the same way as traditional networks that make point-wise prediction. I don't know. Do you have whiteboards on WebEx? I use them in other tools, but
Let me see.
so the idea is that
there's one on a Google box, but a Google
okay.
Meet, but
I can use Inkscape.
there is a notes thing, but it is just
No,
it's just notes.
If I can share my screen, I'll draw it over here. I'll just share my screen again.
I mean, I just wanted to know if your goal, when you think about this epistemic approaches, your goal is to meet the requirements of strict accuracy at the same time of giving the credible intervals.
I don't think that's correct or the thing to do. No, I think like this is your ground truth. No, can you see my screen?
Yeah, yes.
Yeah, this is your ground truth. Not too much. And this is your Bayesian prediction. And it is your deterministic prediction. Then you just you can measure how close you are. To the ground truth. If your prediction is a set, then what performance measure should you be using? Then arguably you should be measuring the distance between the ground truth and the set of predictions, right? And if this is a probabilistic space, then your Bayesian prediction is going to be inside this one, so you're bound to outperform a Bayesian predictor, let's say. But this, what I'm saying here is that uncertainty-aware methods need to be evaluated in a different way. And so I don't think that I think if you look at this from an A point of view, you can say, oh, the accuracy is lower, but how are you actually measuring performance? This is the problem. And a lot of people would be, so it's going to be a lot of work to convince people that they need to abandon certain ways of assessing performance because these are just not suitable for uncertainty aware. Whether you use Bayesian uncertainty or use epistemic uncertainty, it doesn't matter, but uncertainty aware models cannot be evaluated in the same way, in my mind.
Yeah, that's helpful. Thanks.
And that means that sometimes you won't be able to make commit to a specific decision, for instance, and you will hesitate.
True.
And people say, I don't want a network that doesn't make decision or abstains from making a decision. When my reply to that is that if you don't abstain when you don't have enough information, you can make a catastrophic mistake. You can make the wrong decision, and then you know, like those cars, autonomous cars, we make this example in the proposal that didn't recognize a truck, and then they, you know, crashed against it and killed people. You know, you're welcome to always want to commit to a decision, but you're gonna run a very significant risk of a catastrophic mistake if you do so. If you model epistemic uncertainty, you can have a more cautious approach in which, you know, that will tell you at any given time the uncertainty associated with your decision that you need to make and whether you want to commit to a specific decision or prediction or not. So it's not about not wanting to decide, it's about being aware of about information you have and what can that give you, you know? If you so yeah, so I think the principle, the philosophy is quite different.
Yeah, thanks a lot. It makes complete sense. Yeah.
Thank you. So let's keep talking
Yeah.
if you're interested in these things.
Yeah, but I hope it will be fine if I write you an email regarding
Oh
this in
yeah,
future.
no, absolutely. Like I said, that we are very interested in collaborating with new people throughout Europe and outside of Europe. So
Hello,
thanks, Sam.
Hello, could I also ask a question?
yeah, of course.
We're out of time. Continuing this discussion about measuring the efficiency, what about measuring, for example, is there a theoretical guarantee that this approach will not provide wrong results? For
I
example,
think okay. My intuition is that we can get theoretical guarantees that this approach will provide fewer wrong results than traditional ones. So, like I showed in my, let's share again. Sorry, like I showed in my little drawing here. So if compared to Bayesian predictions, for example, Bayesian prediction is a single probability down here. If you use a framework that generalizes Bayesian reasoning, like random sets of belief functions, your set of prediction is going to include this one. So by definition, almost by definition, you're going to outperform Bayesian predictors in any circumstance. So your ground truth still might not be inside your set of predictions. So there still might be a gap, but it's going to be a smaller gap than with traditional methods. So my intuition is that we can derive actually theoretical guarantees that we are going to be less frequently incorrect than traditional approaches.
Thank you. Maybe a small link with the one thing that I was recently working with, conformal learning. I don't know if you heard about it.
I haven't read about it, but I did hear. I think it's from Brookes as well.
Yes, exactly. So one of the maybe interesting points there is that they do essentially the same also prediction with uncertainty guarantees, but there is theoretical limitation, and the person who is using the framework can specify how much errors, for example, are allowed. And the theory guarantees that there will be not more than this predefined limit.
No, that's very interesting. It's something that I'm aware that this is one of the options. So I'd be very happy to look in that direction if you want to. Are you working on these things actively?
Yes.
Okay.
Yeah, I started recently, but I do. Yeah, and there was in fact one seminar here about this topic.
That's very relevant and interesting. So I think my intuition is that most practitioners will not be willing to completely abandon the way they do things. So we need to be gentle with them. And I think we wanna move to a framework that is not so distant from at least Bayesian reasoning, whereas conformal learning is my understanding is based on very different principles. So in terms of the impact, Vox and Schaefer's work didn't have a lot of impact. They published their book in 2004, and it never had the impact that things like belief functions or other frameworks had.
I would just
in this period of time. So there is a danger that if we push for more like esoteric formalisms, despite the theoretical guarantees, they will not follow us. So there's also a societal trade-off here to be understood.
In fact, So in fact, this year's ICML, they had a workshop. It was on uncertainty guarantees, something like that. and conformal prediction was one of the topics.
Thanks for pointing that out. I'm
Yeah.
very happy to look into that and possibly collaborate with you on this.
Oh, great, me too.
Very nice.
Mm-hmm.
Down
Okay.
right alley, so perfectly down right alley.
Okay, then maybe we'll discuss
Please email
the follow-up.
me.
Yeah.
Absolutely.
Thank you.
We are 11, but let me just allow me to sneak in one question about the capabilities at all to encode uncertainty for the evidence, which creates some topologically more complex sets, because it is a kind of question that arises from my collaboration with Sorab, who was asking the previous question. And we encountered the problem, the distinction between the extrapolated and interpolated uncertainties, and then we had some sets of data, and we couldn't too much figure out which part of the let's say we have a new test point, and whether this test point lies within the trained data set or outside the data set. And I believe that when the amount of data or the complexity of the system is higher, then we can hit some exponential growth of the complexity of the description of these confidence levels. And what's your maybe intuition behind this? How do you see these problems from your perspective? Because yeah, I think it's quite important problem to be addressed.
Absolutely. I mean, efficiency is very important. Otherwise, people are not going to use these methods. And I see different possible ways of coping with complexity. Like I said, efficient sampling is one of them. So maintaining a fixed budget in the representation, for instance, if you have use a cradle set of predictions or models, you can select a fixed number of vertices and you keep working on a fixed number of vertices. So instead of having one probability, you're going to have like 4 probabilities or 5. So it's going to be a constant multiplied by the complexity of traditional methods. So there are different ways of constraining the complexity and keep working with a budget. So I don't see that's going to be a particular problem at all, actually. So there are various options. Selecting a particular class of representations, they have a fixed cost. Doing sampling, like I said, there are various options. So I don't see that as a problem at all. Nobody's is thinking about a naive implementation or exponential cost. It wouldn't be feasible. It wouldn't be trainable. So
okay.
I mean, we again working out what is the most efficient way is part of the project, and we are working on that. But I can already see 2 or 3 different avenues for solving that problem. So I don't think that's going to be an obstacle.
I see.
But let's keep talking. I mean, if I have a better understanding of your particular problem, then I can think about it. But keep in mind that we only started the project a few months ago, so we are in the gearing up phase. So the actual work, the interesting part, will start probably in the next year.
But I also keep in mind that you are an expert in the field, so
please, yes, that's true.
Yeah, but we will definitely try to pose the question in a more clear way and contact to you for your comments if possible.
I'll be very happy.
So the time is like 11:10, so I think we should finish today's meeting. Thank you very much, Fabio, for your presentation and all the information that you have passed us and answered our questions. And thank you for your discussion and for questions from the audience.
Thank you, Jakub, for having me. It was a pleasure, really.
Let me invite all of you for the next week seminar, which will be the 3rd part of the lecture given by Margarita Alexandrova. 2 parts are already recorded and stored on our website. So if you were not present in the past, you can update yourself with recording. So have a nice day, and let's stay in touch.
You too, and let's keep our conversation going offline then.
Yes.
All right. Thank you.
Thank you. Bye-bye.
Thank you very
Thank
much,
you.
Fabio.
Guys, nice to have.
Thank you. See you. Bye.